Okay, so for math 3, we're going to go over 1.5 and we're going to go over slide 20 or retrieval problem number 1. And what this is you're reaching back all the way back to, I want to say, a little bit of math 8 when you were in 8th grade. Because that's where square roots come from. And then, but also a little bit of like integrated 1 and 2 when we started using these exponent rules in a little bit of a different way. So let's get started here. Okay, so when I look at this first problem here, it's kind of looking funny because I've got the 5th root here and the 3rd root here, or whatever, the 5th root here and the 3rd root here. So when I'm doing this, when I'm thinking about this problem here, I'm really thinking about rewriting it in terms of exponents, not with radicals. So if you can kind of remember, this is just me off to the side here, x to the 1/2 is equal to the square root of x. And here, right here, is an invisible 2. Right? It's a square root, so it's a 2. Oh, you can't see what I'm doing right now. Hold on. So it's this invisible 2. So if I wrote it out, you would see a little 2 right there. Okay. And so the reason, what you'll notice here, and I'll write one more just for like so you can confirm what you think it is. If I did a 1/5 root here, right, I would put a 5 here as the 5th root. So you'll notice that whatever root is it'll turn into a fractional exponent. I think we talked about this very, very little last week. So if I rewrite all of these in terms of exponents and not square roots, then I can play with these a little bit more. So the first thing I'm going to do is I'm going to rewrite x squared to the 1/5, right? And then times x to the 1/3, okay? And that's not like anything new. Oh, computer's gonna catch up to me. That's not anything new that you're considering right now, so it's okay. Right? So, but the thing is 2 things you need to remember is, what do I do with these exponents right here? And hopefully you're like, oh, I remember that. That's when I multiply. So that's going to turn into x squared with a 5th root there, looks like that, times x to the 1/3. And then you're like, okay, well, what do I do here? How do I work with this? Well, if you remember, this is going to turn into x. And because like they have the same base, then I could just add these exponents. And if you forgot why you can add them, if you consider like x squared times x cubed, right? That just means x times x times x times x times x, right? Which all that means is that's x to the 5th because there's 5 of them, right? There's 5 of those. So what did you do to the 2 and to the 3 to get your 5? Well, I just added them, right? So 2/5 plus 1/3, I'm just going to write that up here, 2/5 plus 1/3, whatever that is, that's my answer. And so we're really done. And then I bring you back to, I don't know, maybe 4th grade when you had to figure out uncommon denominators. No, maybe that's 6th grade. I think that's 6th grade when you actually had to add these 2 together. And so I'm thinking, oh, I need a common denominator. My common denominator is going to be 15. So that's going to be 15 like this. I'm going to add these together. So that, what is that, times 3? So that's a 6. And this is going to be a 5. So this is, my answer is going to be till the 11/15, which looks really funny, but that's your answer, x to the 11/15. Okay, so here it says use properties of exponents. Yeah, we used a lot, right? One of them we used was the fractional exponent is the same as the 5th root, and the 5th root is the same as a fractional exponent. We also remember that when we take a power to an exponent, those are being multiplied. So we got 2/5. And then we use the, if they're being multiplied, what do we do with our exponents? We add them, right? So we use a lot of properties to find an equivalent expression, that is, write your answer in exponential form, that's an exponent. with positive exponents. Yay, that's a positive exponent right there. We're done. Okay. So now I want you to kind of pause this, and then I want you to try your retrieval problems, which are, okay, sorry if you're getting dizzy, I am too, all the way down here, right here. So if you can take a look at that, and then we'll play with them in just a second. Okay, so for this one, so I'm gonna do 3 and 4. It's still the same like thought, if that makes sense. It's still the same thought behind all this. So number one, you got to convert it into the fractional exponent, and then number two, you're gonna play with a bunch of stuff. So I'll start with number 3 first. So this is gonna be a to the 1/6 times a squared to the, that doesn't sound right, sorry, a to the 2/3, and then times a, oh, that's a b, sorry, times b to the 3/5. Okay, so here, over here, number 1 and number 2, they were all the same bases, x, 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 x. Here we have a different base, right? And I'm actually going to go this way so that I don't crash into 4. So here, I can't combine this with this because they have different bases. So automatically, that b to the 3/5 is going to stay. Like nothing is actually going to happen to it, right? Okay, so then I'm going to do this one right here, and I'm going to do the same thing that I did before. I'm going to add these two fractions together because I'm multiplying. So I'm going to go like this. It's going to go 1/6 plus 2/3, right? So, and if you think about the common denominator between 1/6 and 2/3 is, it's going to be a 6, right? So that means 1/6 gets to stay plus, and then this, I'm gonna make this a 6 on the bottom. So 2/3 is the same as what, right? Is the question. 2/3 is the same as what 6th? And so here, remember back in maybe 6th grade, you would multiply by 2 on the bottom, and then you would multiply by 2 on the top, leaving me with a 4. And then you would just add the numerator. So that's 5 over my old denominator, which is 6. So then our answer is a to the 5/6. Good. Okay. Okay, so for this one over here, because our numbers are bases, we're going to try to get them in as many different ways as possible. And so the thing that I want you to think about this one, and number 5 is pretty interesting, so I'll make you do number 5 too, is when you have numbers that have the same base like this, you can have them like kind of like combine exponents, so that's like one base, one exponent. When you have numbers like that have different bases like a and b, you can't let them, I say play together. They don't play together because you don't have the same base, you don't have the same exponent. So they kind of sit next to each other. Does that make sense? So let's do this one right here. And so I already know this one, the square root of 9, I know that number, that's 3. So I'm just gonna write 3 off the bat right there. And then it says the 5th root of 32. And because I know my roots, I know that this number is clean. So I'm going to show you how I break this down. So I'm going to go over here to the 32. And this is how I break down square roots. I just say what times what gives me 32. And someone's like, oh, it's 4 times 8. And then, okay, 4 is what? 2 times 2. And then 8 is what? 2 times 4. And then 4 is what? 2 times 2. So if you look, now I want you to pretend that this is a branch. I want you to look at all the edges of the tree. So this is a tree. And it's like an upside down tree, right? Do you guys all see? Like here's the roots, and then this is like these are all my little branches. This is the ground. It's upside down. Here's the roots if you want, right? So I know, great drawing of a tree. But then this is like the actual tree part. Like if you can imagine, like the tree is like this. It's upside down, right? Okay, so if I look at the edge of my branches, the 2, 2, 2, 2, 2, right? 2, 2, 2, 2, 2. I'm looking for a set of 5, right? A set of 5. Oh, it can be. Thank you. Okay, a set of 5. So 1, 2, 3, 4, 5. Once I have a complete set, I can take that number out of the radical. So if I'm asking what's the 5th root of 32, it's 2 because 2 to the 5th is 32, right? So really quickly, the reason why the 5th root of 32 is 2, it's because 2 to the 5th is 32. Okay, so here, I'm just going to write a 2, right? So I have a 2 here, and I have a 3 here, and then that brings me to 27, and I'm like, wait a second, I know the cube root of 27. So again, I would do the same exact thing, right? And then I think that the cube root of 27 is 3 because, and so I'll just write this over here, because 3 to the 3rd is 27, right? So the 3rd root of 27 is 3 because 3 cubed is 27. So then I just multiply these. Yep, you just multiply them. So what is that? 6 times 3, that's 18. So our answer here is a little bit cleaner looking. It's 18 than this like a to the 5/6 and b to the 3/5, right? It looks very like, ugh. But this one's clean. It's like 18, right? So here, this is pretty interesting to simplify because you can get numbers into their perfect roots, right? So I'd like you to do this one as well, this number 5 right here, specifically because you could do this one actually in a couple of different ways. And I'll show you one of the ways. So go ahead and pause and try that one. Okay, so for this number 5, the reason why I'm interested in doing this one is because you can pull these all to be the same base, even though 8, 16, and 2 don't have the same base, right? So I'm going to change these so that they do have the same base. But first I'm going to rewrite them with fractional exponents. So this is 8 to the 1/4 times 16 to the 1/3 times 3, oops, that's a 2, 2 to the 1/6, okay? And so the common base that all of these 3 have here is 2. So now I'm going to rewrite my bases in terms of 2. So that would be, so this is going to be something to the 1/4 times something to the 1/3 times, well, this is just going to stay as 2 to the 1/6. And I'm going to rewrite these numbers 8 with a base of 2. So I know that if I multiply 2 times 2 times 2, I get 8. So therefore 2 to the 3rd is 8, right? So I'm going to write 2 to the 3rd here. And same thing with 16, it's just 2 to the 4th. And then we get this like kind of like interesting problem here, right? So now we can go back to, okay, well, what do we do when it looks like this? And hopefully you're like, oh, yeah, we multiply. So then we go this way, right? So we get 2 to the 3/4 times 2 to the 4/3 times 2 to the 1/6. Okay, so the same rules apply like here as in here, which was all you really have to do is just add these numbers, right? Get them in the same denominator. So here I notice I can get them all in a denominator of 12. So I'm just going to add that along the bottom there. So 3/4 plus 4/3 plus 1/6. And then I want all these to be a denominator of 12. And so I'm just going to make them one big fraction. So this first one's times 3. Times 3. And then so that means I'm going to multiply the top by 3. So that first one's going to be a 9. Okay, the second one is going to be 3 times 4 gives me 12. So I'm going to multiply that by 4. So that's 16. And this last one's going to be times 2. So I'm going to add plus 2 here. And so whatever that is, 25, 26, 27. So my total answer is 27 over 12 with a base of 2. Okay. We don't want mixed numbers here, right? We don't want mixed numbers. And if you're like, oh, but Miss Johnson, can't we simplify that fraction? Yes, right? So this is 27 over 12. We can simplify that fraction. So that's what, 9 over 4? Yeah. And so I can rewrite this to be 9 over 4. Oops. Oh no, what happened? Hold on, my iPad is being cuckoo right now. Nope. Sorry, it kicked me out. So you can actually leave that fraction as 9 to the 9/4 rather, if you'd like, or you can leave it as 27/12. That's fine too. But probably leaving it simpler is better than anything. Right. So I would write it as final answer is 2. Oops, that's not gonna let me write right there. It's like going crazy because I'm writing on the edge. Hold on. So 2 to the 9/4. Okay. And then so that should be pretty good. So the last problem I'm going to do for this video is going to be this one. And one of the things that in terms of exponents and review and square roots and stuff is I want you to remember the definition of what cubed actually means, right? So the definition of cubed actually means I need 3 of those. So I'm going to write that to 5 to the -4 over 5 squared times 5 to the -4 over 5 squared times 5 to the -4 over 5 squared. Now, somebody like maybe you're thinking, oh, but Ms. Johnson, I could kind of like distribute that. Okay, as long as you don't make any mistakes, because just make sure that you always go back to definition. You know what that means. So along the bottom, that makes sense. 5 squared, 5 squared, 5 squared. I know what that's going to be. That's just going to be a 5 to the 6th on the bottom, right? And then what do I do with this negative exponent? So if you've watched in the previous videos about what negative exponents actually mean, so negative exponents actually mean dividing by 5 that many times. And so if you kind of look, it's on the wrong side of the fraction. So I'm going to put it down here. I'm going to divide by 5 4 times and just put it on the bottom right here, right? Because that's what a negative exponent means. These negative exponents here just means these ones here. But I have to do it 3 times because that's what it says to do. So I'm going to do it 1, 2, and 3. So what goes on top is the weird question, right? Well, 1 goes on top, right? Because there's invisible 1s all over the place, right? And they appear when they need to appear in order to be a placeholder, kind of, so that we don't have a blank numerator. And then you would just simplify this here. And so you're remembering, oh, Ms. Johnson keeps saying that whenever I have the same bases and I'm multiplying, I just add my exponents. Exactly. So then we write our final answer as 1 over 5 to the, so let's see, that's 10, 18. That's 5 to the 18th. Okay, let's see if we follow directions. Use properties of exponents. Yes, we did. To rewrite the expression, write your answer in exponential form with positive exponents. Yep. Done. Awesome work. Strong work.